We're going to do number 19, and we're going to do number 37. So number 19 is very math heavy, very heavy on algebra, and just doing some manipulations. It's not really testing much physics. But they give us this electric field due to a long straight wire. E is 1 over 2 pi epsilon naught lambda over r. So I have a wire, and then I'm going to take that wire and I'm going to start moving with it. So this stuff is actually applicable. It actually works for calculating fields that are happening, say, inside your phone. Your phone's got wires inside of it, so if you want to calculate the fields that are moving around in your phone to make sure that they're not going to burn your whatever off as it's in your pocket, as you're walking, you can calculate the fields when you start moving these things. Okay? So this does have practical applications. So we're going to start moving, and we want to know what is the current that is produced inside of this object, inside of this long straight wire. So what's the definition of current? I equals dq, Dairy Queen, over dt. Still haven't got my frickin' Dairy Queen. Yeah, I think it's, after the cardiologist. Not before. Right, I'm cramming for my cardiology appointment. So we have, we have a charge that we're given, but we're given charge in terms of lambda. What is lambda? Charge over distance, charge over length. Q over x. So I can actually take this equation I have for current, and I can put it in terms of the current that I was actually given, in terms of the charge I was given. I was given the linear charge density, so I need to rewrite this dq in terms of the variable I was given, in terms of lambda. Okay? Taking this wire, one other thing they gave us, it's moving at a velocity v. So that's the speed. So I need to rewrite this lambda in terms of q. How do I get q alone? Multiply both sides by x. So q is equal to lambda times x. How do I get the derivative of q? What is dq? Lambda times dx. First times the derivative of the second, plus the second times the derivative of the first. Product rule.
But do you use the second one because
What is d lambda? It's a constant. So what happens to that? Goes away. Gone. So now dq is lambda dx. So in this charge equation, I have I equals dq, which is lambda dx, over dt. So I have lambda, I have dx over dt. What is dx over dt? What's a change in position divided by a change in time? That's velocity. So this current is lambda times velocity. There's your answer. And part B, we're asked to prove that B equals mu naught epsilon naught E times V. I hated these questions when I was in college. Oh, maybe I will. My teachers never showed me how to do them, though. They were awful. So, B. This is a long straight wire. What does B do to a long straight wire? Mu naught I over 2 pi r. Okay. I just found what I was. What is I? I is lambda v. Mu naught times lambda times v over 2 pi r. I was also given an equation that describes the E. And I know I need to get an E in here somehow. I was given that E is equal to 1 over 2 pi epsilon naught times lambda over r. What I can do is I can see, oh, E relates to the lambda, so I can get rid of lambda. Yeah? I don't have any lambdas up here in the equation I'm trying to prove, so I want to get rid of lambda. So to do that, I can solve my E equation for lambda. How do I solve that for lambda? Multiply that whole denominator over to the other side. So then I get that my lambda is equal to E times 2 times pi times epsilon naught times r. And I can plug that right in. So B is mu naught times E times 2 times pi times epsilon naught times r times V, all divided by 2 times pi times r. Let's cancel stuff out. I have a 2 up top and a 2 on the bottom. I have a pi up top, I have a pi on the bottom. I have an r up top and an r on the bottom. Cancel all those things out. And I got my B is equal to mu naught times E times epsilon naught times V. Is that what I wanted to prove? Yep, proven. We're done. Okay. Done. Whoa. It's a good reaction. Okay. This would be biatch. Instead of biatch. This is a biatch. Any questions on that one? No? All right, now let's do the one that everybody has questions on, I'm sure. 37. Did anybody successfully solve 37? No? Let's do 37. So I have a coaxial cable. What is a coaxial cable? Do you have coaxial cables anywhere? In bridges they use it. In TVs they used to be it. TV cables used to be coaxial. Now they're HDMI, something fancier. But they all use the same kind of process. They all use the same kind of theory. And we're going to see why we build cables this way. So I have a cable that's in the middle. This is a cable core, and it has a current that's flowing in one direction. And this cable has a radius, we're going to call it R1. And then outside of this, I have another cable. But that cable that I have outside of this is a cable shell. So this is a solid cable, the other cable is a cable shell. Colorful candy shell. So that colorful candy shell has an inner shell. We'll call that R2. And an outer shell that we'll call R3. We could think of it like this. Imagine this is a wire. We'll get a bigger wire. Imagine this is the bigger wire. This is the outer shell. So that inner piece of cardboard, the cardboard part, that's a distance R2. And then the outer part, the outer edge, the blue part, it is R3. Okay? And then through the middle of this, I have a solid wire. Yeah? You all picture this. Solid wire in the middle. So this would have a radius R1, completely solid. R2 would be to the brown cardboard part, and R3 is the blue cardboard part, the outer part, outer shell. Okay? And in that outer shell, we also have a current flowing. So there's my outer shell. The current flowing in the outer shell is the same magnitude, but opposite direction as what's in the inner shell. So one current is flowing to the right, in the middle solid wire. The other current is flowing to the left in that outer shell piece. Okay? Okay. Now we are asked, what is the magnetic field? How would I find the magnetic field due to this? What equation should I use? If you have no clue, there's a good hint inside the textbook. If you look at what section it's in the problems, it'll actually tell you this is an Ampere's law section, so we probably want to use Ampere's law. It's no other idea. Look at what section of the book it's in the summary. Can't do that on the test. Okay. So what is Ampere's law? Integral of B dot ds equals mu naught times I enclosed. And we're just going to repeat this again and again and again for every single region that we're inside of. We need to find the magnetic field if R is less than R1, if R is, greater than R1 but less than R2, if R is greater than R2 but less than R3, and if R is greater than R3. So it's one problem, but they gave us how many different parts to it? Four different parts. Stupid physicists, that's what we do. My qualifying exam to decide if I got a PhD, I had part A through Q on one question. That's horrible. Horrible.
Something like this?
Huh?
You had something like this?
Oh no, much harder than this.
What is it?
It was quantum physics. How many have taken PChem? Imagine the hardest problem in PChem and kind of double that difficulty and do that Q times. It was awful. It's awful.
But you got it.
Yeah. Did I tell you the story of my qualifying exam?
No.
So the way these qualifying exams work, if you don't know, this is to decide if you get a PhD. You have to prove that you know all of physics. And there were 3 different sections on it. There was classical physics, which is basically last semester. There was electricity and magnetism, which is what we're doing now. And then there was quantum physics, which is stuff that we never even get to, don't want to think about. Okay? So I had to do each of these sections. And the way it works is you take the exam, and then a panel of faculty get together, they look at your exams, and they decide, did you pass or did you not? Usually passing score is considered, did they get a 50%? But a lot of personal preference comes into play, so if a professor doesn't like you, they will say your 50% is not equivalent to somebody else's 50%. So they will fail you. Different professors can take you. Huh? No. There was a professor there that hated me. She actually was in charge of quantum physics. She hated me because I did research. So I traveled and had to miss her class twice to go on observing trips. And I get no choice in that. I apply for time competing against thousands of other people. If they give me the time, I have to go. And I had to miss her class, so she hated that. Yeah, not a big fan. So I actually took the qualifying exam and she failed me on the quantum physics part. Yeah, my score was higher than half of my classmates, but she failed me on it.
I hope she watches.
My percentage, I think my percentage on the quantum physics part, the first time I took it, was a 60%. And one of my friends, she got 45%, and they passed her. Yeah, so very unfair. And the qualifying exams, the way this works, you get 2 chances. If you fail the second time, you're out. No PhD. Ever. Well, you go back and try to get it from a different school. But I was at Clemson. It was an easy school. So no chance to find an easier school. So I have to take the qualifying exam again. And I know this woman has it out for me. So I study quantum physics like crazy. I'm very good at quantum physics now. I took the exam. They graded it. I got a 98% on quantum physics.
Oh, she can't fail.
Usually
now.
50% is passing.
Wow.
The only students that ever get 98%, they're always Chinese students. They are the best students. Okay? In engineering programs, that's the way it works. It's standard. There were professors in the room that didn't know me. And There were several, because the physics department is very big, right? And I was in the astronomy department, so lots of faculty didn't know me. And they're looking at my paper and they're like, who was this Eric Bubar? Is he a Chinese guy? No, I was not. Aced it.
So she has to pass.
Harder than this stuff, but I'm a physicist, so I should be able to do it. Okay, so let's talk about this. Let's figure out how we do these problems.
And when did you get your PhD?
What?
What year?
What year? 2009. I started in 2005, got it in 2009. The average is 7 years. I did it in 4 because I was sick of her.
So she had to pass you though, right? Like,
Oh yeah, she had no trust.
I mean, he's here today. You're here today.
So, really,
did you rub it in her face? Like,
no. I didn't go talk to her at all. I think she was pregnant, and then when I passed, and then she had maternity leave for like 2 years. So I finished and left. I wasn't going to go back from New York to rub it in her face. Okay, so how do we do this problem? First, we need to figure out what is Ampere's law for inside of this first wire. So my radius is less than R1. So this blue wire, I'm inside of this. I'm inside of the wire. It's a solid wire, but I'm inside of it. So if I can draw that, let's draw it in a different color. What color do you want? Purple. So I'm inside of here. Very hard to see. That's a tiny, tiny little R. So I'm in a little piece of this wire. So I'm not enclosing all this charge. I'm enclosing a portion of it. The purple is the amount of wire that I'm enclosing. So that's any piece of this wire inside of here. Okay. So I'm enclosing all the current that's inside of the purple part, but I'm not including the current that's inside of the blue part that's on the outside. Okay. That's the only amount of current I need to include. So that's my I enclosed, and I need to figure out what that is. This is the hardest problem with these problems, figuring out what is the I that's enclosed. The left-hand side of this is always related to your Amperian surface. My Amperian surface is just a circle. So it's B times ds. ds is how far it takes you to get around a circle. What is that called? Going around the outer portion of the circle. Circumference. And what is that? 2 pi r. B times 2 pi r. More or less, any kind of Ampere's law problem I give you, the left-hand side is going to be B times 2 pi r.
wow.
Okay?
Watch, she's gonna give us something else.
Similar to Gauss's law. In Gauss's law, I only gave you one kind of Gauss's law problem, really. Sphere.
Yeah.
And what did you get on the left-hand side for a sphere? E times 4 pi r squared. Okay? Here you'll get B times 2 pi r. Done. So now this is equal to mu naught times I enclosed. Now, this current is uniformly spread throughout this wire, so I can figure out the enclosed current by taking a ratio. So I can do I enclosed over I total is equivalent to the total area that's enclosed over the total area. This will always work as long as your current is uniformly spread. The enclosed current over the total current is the same ratio as the total enclosed area divided by the total area. Okay? So I enclosed is equal to the area that's enclosed. So that's the area of the little Amperian surface that you drew. What is that area? What Amperian surface did I draw? I drew a little circle.
Oh.
What's the area of a circle? Pi r squared. And what radius is that? What is the radius of my Amperian surface? Same as it is over in the left, it's little r. Yeah? Okay. Divided by the total area. What's the total area of all the charge? If I would include all that wire. Is what? Same thing with R1. Pi R1 squared. And then I multiply my total current to the other side. I enclosed, multiply the I over here. What happens to pi? Goes away. Everybody's always sad when pi goes away. Then there's no more pi to eat. Yeah, is Math Club doing anything for Pi Day? Is there a Math Club?
No, but I know the R one your algebra class.
Your class.
Yeah. Sorry.
I got science club. Are we getting anything?
We should trump them.
We could do like a math major and science club.
So I enclosed
Like our math honor society's business.
is R squared over R1 squared times I. We have class on Pi Day?
Wait, isn't it spring break? Oh, just kidding. No.
It is spring break, isn't
I was
it?
gonna say.
Yeah.
We could do like a post Pi Day.
No Pi Day.
I was so confused. What's
We had an event for like
Okay, I enclosed is R squared over R1 squared times I. So now this goes right back into your Ampere's law equation. This gets plugged in right up here. So B times 2 pi R equals mu naught times R squared over R1 squared times I. So now my magnetic field, if I divide that 2 pi R to the other side, 1 over 2 pi R times mu naught times R squared over R1 squared times I. I could simplify this, right? I could get rid of an I. You don't have to. I'm not going to make you simplify. There's your answer. There's your B. This is for R is smaller than R1. Okay? So this is probably the second hardest part of the problem. Next part. There's always more. R is greater than R1, but less than R2. Right away, we can jump to B times 2 pi R. We know that. Equals mu naught times I enclosed. Let's go back up to our picture. Let's explode this up. We're going to go back down. Let's do this in red. So in red, if I'm between R1 and R2, I'm going to be in here. Purple is for the first part, red is for the second part. How much current am I enclosing inside of this red tube? All of this blue wire. How much current is in the blue wire? I. How much current is in between the blue and the green? Nothing. So how much current is enclosed? I. So what's I enclosed? I. So this is B times 2 pi R equals mu naught times I. So B is mu naught times I divided by 2 times pi times R. Done. That's not so bad, right? That was pretty easy. Now let's do between R2 and R3. What do I have on the left-hand side of the equation? B times 2 pi R. What does that equal to? Mu naught times I enclosed. So now I have to figure out what is the I that's enclosed within this surface. So let's go back, let's draw the surface, and we'll see what we have. This will be very zoomed in again. We're going to go with gray. So now I'm in between this R2 and R3. Pictures get very, very busy. How much charge is enclosed inside of this gray? All of blue, right? All of I. So I can include that. And then, do I have all of this other I included? I have a fraction of it, right? That I up here is going all the way between green and yellow, and I'm only including a portion of that. So I need to scale it. How do I scale it? Same way that we did before. Let's go again. Okay. So I enclosed. Is equal to I, then I'm going to do minus. Why am I doing minus? Because it's going the opposite direction. So the current that's in the outer part of the wire, and this part, is going the opposite direction. So I have to subtract that off. Yeah. And then I have to scale. I have to scale this appropriately. So I have to do the area enclosed over the total area times the total current. Same scaling I did in part A, just going to have different areas because the wire is different size. Okay, so let's look. I see nodding heads, that's good. I'm zooming around so much, I gotta write this on the board. Area enclosed. What is the total area that's enclosed inside of this? So what's the outer part of this? What's this radius? This gray line. R? That's my Amperian surface. Your Amperian surface is always pi r squared. And then what's the inner surface? What's the green? R2 minus pi times R2 squared. And then I have to divide by the total area. What's the total area? Where all the current is spread out throughout. So that's the outer one, which is pi R3 squared. Minus the inner one, the inner green one. What's the inner green one? Pi R2 squared. And then if I want I enclosed, I multiply all of this times I. So that is, I think somebody's going to get motion sickness watching this on YouTube. So this is I enclosed equals I minus pi r squared minus pi r2 squared over pi r3 squared minus pi r2 squared, all of that times I. Looks like a mess. Leave it as a mess. Don't try to simplify it. Your book simplifies it. No reason to do that. So now my B is equal to mu naught times I minus this big giant mess, pi r squared minus pi r2 squared divided by pi r3 squared minus pi r2 squared, all of that times I, and then divide all of this by 2 pi r. There's your answer. Big fat hairy mess. Whatever, let's leave it like that. Okay. Now, if R is greater than R3, what do we get? Inner wire, I have current going that way. Outer wire, I have the same current going the opposite way. What do those add up to? 0. So if I'm outside of the wire, how much current am I enclosing? 0. What is the magnetic field? B equals 0. This is why we use these cables. Electricity creates magnetism. If you use this kind of cable, then the magnetic field outside of your wire is 0. So it won't interfere with other electronics, other kinds of equipment. It shields itself. Okay. You need to use this kind of structures when you're building NMR magnets. Anybody use the NMR? They don't let me near it anymore. Because I do fun physics things. You can go in there with like a screwdriver tied to a string, and if you hold it up close enough, it'll actually be pulled and it'll just hover in midair. You can take paper clips and they'll line up against the magnetic field. Maybe I'll see next class if I can sneak in there, get some demos done, and kind of have you come up table by table and break the NMR. I think that would be more useful than whatever the heck they do with it. Show you some cool stuff. Okay? That does seem very science clubby.
Yeah, very good.
Sketchy.
Yeah, that works.
La, 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 la. Okay. Now let's do some more right-hand rule practice, and then I want to show you a demonstration that if you can explain the physics behind it, I'll give you 5 extra credit points on the second exam. Huh? That's in addition to last class. It's going to be a new kind of thing. It's a new demonstration.
That's like 10 points right there.
That's like 10 points right there, which means your next exam is going to be hard as shit. Okay, so let's do the right-hand rule.
What?
Right-hand rule. Let's practice the right-hand rule. Okay, it doesn't, but I'm going to be bouncing back and forth, so this might not be a good come back to video. What directions do you want to do?
X, Y.
What? Give me a direction for V. Up. Velocity is going up. Give me a direction for B.
Down.
B is going down. What does the right-hand rule say for the magnetic force direction? What is the cross product of anti-parallel vectors? 0. No force. Done. Let's do another one. Give me a V. Nope.
Down.
Don't want diagonals. I can give you diagonals. Down. Okay, V is down. Okay. That's V. Where does B go?
Down. Sideways.
B is going down? Okay. We really want easy. What's the magnetic force? They're both going down. So what's the magnetic force? What's the cross product of two things that are going down? What was the cross product of a thing that was going down and a thing going up? 0. What's the cross product of a thing going down and another thing going down? 0. No force. Cross products for vectors that are parallel or anti-parallel are 0. Always 0. Give me another one. Where does B go?
Down.
Left. Where does B go? Up. Okay, now we can actually do one. Okay, B is going to the left and B is going up. So you take your fingers, point them in the direction that B is going. And you want to make sure you use your right hand. Why do you use your right hand? Because it's the right hand rule. So I take my hand and I point it to the right. I want to rotate my hand so that I can bend my fingers in the direction of B. How do I do that? Turn it. And I bend my fingers. I bend my fingers up. What direction is my thumb going? Into the board. If I'm going into the board, what direction is that? Negative K. Force is in the negative K direction. We denote that like an arrow that's flying away from you. You ever seen an arrow? It's got the little feathers. So an arrow is flying away. Versus if it's coming towards you, it has a little point. We can do that demonstration next class too. Start killing students. For those on YouTube, there are like half of them are volunteering.
What does that say?
F with the X. That means it's going into the board.
Isn't that basically
negative k hat. Okay. Give me another one. What direction is V going? Right. Where's B going?
Does the same thing. That's the left. Yeah.
Okay, V is going to the right. B is going down. What direction do I bend my fingers? Bend my fingers down. What direction is my thumb going? Into the board. Those arced up a little, sorry. I'm not trying to, nothing political. So exactly horizontal. Bend going into the board.
Well,
So negative k.
So it's another negative K?
Yep. Do another one. B is going up. Let's do B is coming out. B is going up. Where do I put my fingers? B is going up. Where do I put my fingers? Up. I want to bend my fingers so that they're coming out. Where do I, how do I do that? If I bend my fingers, they're going in. How do I get my fingers to bend out?
Turn your hand.
Turn my hand. Okay, bend my fingers. Coming out. What direction is my thumb going?
Right?
To the right. Force is in the I hat direction.
So what does that little circle dot thing mean? Is it
Circle with the
six
dot
seven,
is
eight?
coming out. It's an arrow coming towards you.
Listen, Linda.
Let me show you a different way to do these. So you're not always given a picture that looks like that. Sometimes you're just given a letter. You're given maybe I and K. I cross K. How do I do this? So I is going this way. I bend my fingers so that they're coming out, so I have to rotate my hand around. I bend my fingers, coming out. What direction is my thumb going?
negative J.
Down, negative J. So this gives me negative J. There's a different way that I do this. If you have a different way that you use that, as long as it's giving you the right answers. This is an approach that I taught a couple years ago, and students seem to like it. So let's see if you like it too. I think we did it last semester too. I, J, K. I, J, K. So this is the normal alphabet. If I'm going the normal direction of the alphabet, I get a positive. Or if I go the opposite direction of the alphabet, I get a negative. So, how do I use this little key that I can put on my cheat sheet and write down? I have I direction. So I come down to this, and I see I, and next comes K. And the top one, if I look at I, the next variable is always J. So I can't use the top thing. So I have to come to the bottom. If I look at I look at the next variable, I have K, good, I can use this one. I go to the next one, I get J, and since it's the opposite alphabet, reverse alphabet, I get a negative J. Give me another one. Negatives, do everything with positive and then toss the negative in at the end.
So if it was. Okay.
JK? Let's do J cross K and then we'll do J cross negative K. There's plenty of time. Meet all your demands. J. So I can use my hand, and J is going up, bend in the outward direction. I'm going in the I direction. I can also see that down here. J, K, I comes next. That's a positive, so it's positive I. Now you want J cross negative K. So J cross negative K. I do J. J is going up. Negative K goes in. What direction is my thumb pointing now? Negative I. Now if I pull that negative out, so I do negative J cross K. J cross K is I, and I get my negative I. So you can just pull out any negatives, do the cross product with this, and then put the negatives back in. So we can test that. Let's test that. Negative j cross negative k. If I pull both those negatives out, then I just have a positive j cross k and it should get I. Let's do it with your hand. J, well, negative j, what direction do I put my hand? Point it down. Negative k, what direction do I do? I have to bend into the board. I bend into the board. What direction is my thumb going? To the right, positive I. So I get I. Yeah? Right hand rule. Now, what if I give you an electron? What do you do with this?
Make a negative.
Take the opposite sign.
Left it.
Okay? Or use your left hand. Yeah, I don't recommend using your left hand.
No, I've tried it. It's really
If you're going to break a hand, break your right hand. If you break your right hand, most of you are right-handed probably. If you break your right hand and can't write, then you can't take exams.
Like actually.
No, that's not true. I did that when I was
No,
in
not
elementary.
true.
My teacher said to write with one hand left. We're so like a solid 2 months.